Hi everyone, my name is Sarah Waldo and I'm a graduate student at WSU in the Lab for Atmospheric Research, and I'm here representing the Objective 2 monitoring team. I'm going to give a talk on the integration of chamber and tower methods with crop cyst modeling across agroecological zones within REACCH. So I have to thank Claudio and Kirill for giving me some background information that you guys are all up to speed on now for getting more into how these can be integrated. So how does this fit into the broader REACCH project? This topic directly addresses one of the primary goals, which is climate change mitigation. Agricultural soils are a source of the greenhouse gas N2O, but they can also be a sink for CO2 by building up soil organic carbon. Determining the current baseline of greenhouse gas uptake and emissions gives us something against which to compare uptake and emissions under future climate scenarios. And additionally, measuring at multiple sites and under multiple treatments will inform the impact of management decisions on the greenhouse gas balance of different cropping systems. But in order to realize the potential of cropping systems to sequester greenhouse gases, we need to compile greenhouse budgets across the region. And in order to do that, we need spatial and temporal integration of the greenhouse gas measurements. And this, in turn, rests upon the measurements from the static chambers, from the flux towers, and then the simulation and extrapolation, or the integration, through the crop cyst model. So now on to some of the key concepts and processes. I can go over this really quickly since Kirill talked about this at length. But in this presentation, I'm going to talk more qualitatively about the measurements and models and sort of key concepts underlying how they fit together. So the chamber system consists of 16 automated chambers that collect data on CO2 and N2O emissions, as well as auxiliary biomet information like soil water content and temperature. They provide short-term point-scale data. One of the main advantages to the chamber system is that you can set up these matrix experiments of different treatments that sort of acts as a microcosm of the different management strategies across the region. But some of the key drawbacks are that they're limited in the representation of spatial and temporal variability, and they're not well suited to measure carbon dioxide uptake. This recurring theme of spatial and temporal variation and spatial and temporal integration is really important to the integration of the chambers with flux towers. So the flux towers can address larger spatial and temporal scales because they use the eddy covariance method that measures exchanges of carbon dioxide, water vapor, energy at the field scale continuously. We also have one site, so we have 4 tower sites across the region, one at Lind, 2 at Cook Farm, and 1 at a high rainfall site outside of Moscow. And one of these sites we have set up to measure nitrous oxide fluxes, and we're trying to characterize these N2O bursts. So now onto some examples of the chamber and tower data. Kirill already presented these, so that's another maybe place for integration and communication between the objectives is what figures you're going to have in your presentations to save time. But the key thing to take away from this is, like Kirill talked about, just the sort of erratic behavior of N2O. This high variability is called hot spot and hot moment behavior. And that's just when a small area or a small amount of time can disproportionately contribute to the budget for the whole year. And so that's been a challenge to measure and to characterize. And even though I'm kind of biased, I work more closely with the flux towers, so I'm going to talk about how the flux towers can fill in all the gaps of the chambers. But that's one area where the chambers can help out with the flux towers because the towers are less sensitive to measuring N2O. So now on to some example data from the flux towers. This graph is showing a time series of half-hour fluxes measured at Cook Farm over the whole growing season. The positive values indicate net loss of CO2, so respiration. And the negative values indicate uptake of CO2 by photosynthesis. So you can see over the winter and before the growing season starts, it's around 0. And this red line is the daily average. And then once it gets to be around May and the wheat starts to shoot up, there's this big uptake of CO2. And if we just integrate that over the growing season, so just add all those fluxes up, then we can calculate the total carbon uptake of the season or the net ecosystem exchange, or NE. So now on to how this can be integrated with CropSyst. The chamber systems directly measure N2O, or total identification, whereas the CropSyst model determines total identification and partitions between N2O and N2 by looking at, by using different inputs of temperature, soil moisture, and other parameters. But the data from the chambers and the data from the towers can be used to calibrate and evaluate the model. So you think that you have this relationship between soil temperature and moisture inputs that will lead to this output of N2O, but the chambers are actually measuring that, and so that can be used, like I said, to evaluate the model. And then again, going from the small sort of step-by-step scale to the larger scale, the tower data can be used to evaluate the CropSyst model on the field scale and at larger time scales. So the CropSyst outputs will be greenhouse gas emissions pertaining to the chambers and towers, will be greenhouse gas emissions and soil organic carbon changes across the agroecological zones and cropping systems for current and future weather conditions and atmospheric CO2 projections. Which brings us to the deliverables and impacts of this integration. One is the CropSyst model run outputs, but another is just the chamber and tower data sets themselves. These, we just talked about all the data management, so these can be put online, made available for a lot of people, and be further analyzed for some really important information. And this effort requires collaboration between 3 objectives. In a nutshell, the cropping systems inform how to best measure what we're trying to measure. The monitoring feeds into the quality of the modeling, and the modeling outputs inform best management practices for the cropping systems. Thank you.